Hello, my name is Daniela Klein. I'm doing a PhD in Stockholm at KTH. And today I will present the results of a master thesis that was conducted under my supervision. And my PhD supervisor was the examiner of this master thesis, and this is Jonas Faleskog. So this is my agenda, and I will start with the fundamentals and background to this project. So in brittle materials, one brittle mechanism can be cleavage fracture. And here, cleavage fracture is, it has several steps. And here I have two steps, or here I consider two steps. The first step is where the microcrack nucleates. This often happens by inclusion cracking or the bonding. So here, this is an SEM image that I took together with people from in Finland. Here we have an oxide, and if you follow the river patterns, which are these lines here, you can find the initiation point, which was here the site of this inclusion. And this cracked by the bonding. This was initiated by the bonding. And this is typically a strain-driven process. The next step is then crack propagation. So if we have the microcrack, then the crack goes into the crystallographic planes. And this is typically rapid and catastrophic. And we assume it's a stress-driven process. And because the nature of these inclusions and microcracks can be quite random, like where are these inclusions placed, and are they do they have a certain angle? The fracture toughness that we measure in this brittle materials is then quite scattered. You can see here we have different fracture toughnesses that we measured in this material. And this is a really large scatter, actually. And this is then ranked. The experiments can then be ranked, and that's how we get on the y-axis the failure probability. And this can then be tried to be modeled with a weakest link model to try to we fit it, and then can try to predict other specimen geometries, for example. So what is weakest link modeling? And it's based on the idea that we have a chain with different links. Every link has a known failure probability. The probability of survival of the chain is then 1 minus the failure probability of the chain. And because all the links are independent, we can express it in this way and rewrite this in terms of the failure probability of the chain. And we always have 1 minus the exponential function of minus the sum over all the failure probabilities of the chain links. And if we extend this now to continuous volumes, we integrate, or we replace the sum here by the integration over the volume. And here we have something called a hazard function. So this is the failure probability in the material points. So the unit is per volume. And this depends on the mechanical fields, the stress and the strain. Some examples are the Brittle model and the Faleskog model, which were used in this work. So the Brittle model, here we have modified it a bit, where we are using the average first principle stress. So it's again 1 minus exponential function of over this. It is a Weibull distribution. And here, this quantity is the Weibull stress, and it's expressed like this. The red parameters are the parameters that we will fit. And sigma 1 is the first principle stress, but we use an average value. So we basically average over a certain value, or we average the stress tensor over a certain volume and calculate the first principle stress from this. The Faleskog model, which was developed in 2002, has now the assumption that the strain cannot be negligible in these models, meaning we think that these two steps, this nucleating a microcrack and propagating the microcrack, are statistically independent, and hence the failure probability can just be multiplied in this case. So here we assume for an increasing, or we assume a linear function basically for the nucleation of microcracks. And this is now the function for the stress-driven part of the process. And again, we use the average first principle stress. So the background to this project was then that in our department, they developed a weakest link model. And this was fitted on SAN-B specimens, so single-edge notched band specimens. And it worked really well for those. Then when I started my PhD, I started doing these round notched bar tests. So basically a round bar with this notch that was produced by EDM. And EDM made a extremely, like it was in the mic, like I think 300 microns was this height. And you can see again, the experiments show that we have to scatter. Technically, we should be able to fit this. But the model that was used, that was fitted on the SAN-B specimens, severely underpredicted or severely overpredicted the failure probability. So we were thinking then what was the reason for that? One idea was maybe it's due to the heterogeneity in this material because this material was a weld. So maybe this was fitted on some part of the weld that was particularly weak or less tough. And this is my PhD project basically. But another idea that was always at the back of my head was that what if this was a problem because of the notch effect? So maybe instead of having a fatigue pre-cracked specimen, this notch might have an impact that, well, so we cannot use the weakest link modeling anymore. So the question was, can weakest link models, or the ones that are existing so far, predict these notch effects? And if we want to do this as a master thesis, we cannot use this material that is already heterogeneous and aged. And so, well, we have to find some material, and this is where Udeholm, one of our sponsors, came in, or they sponsored with giving us the material. So they have this high strength steel, which is called H13 modified. It is a tempered martensite microstructure. It is brittle at room temperature, and they have been using some heat treatment to achieve this. And they were quite secretive about the material in general because they are still a research project. And we have obtained, we have done these tensile specimen or tensile tests to obtain, well, the stress and strain curve, and from there obtain plastic parameters. The experiments that were then done or conducted by the master thesis student, Gustaf, were then these 5 sets. So the first one was a SAN-B specimen again, with a deep crack. It was 11 specimens. Then the second one was a short cracked specimen. And then the next 3 specimens were this geometry with a notch. And we had 3 different notch radii. This time we used different thickness of the wires in the EDM and measured it afterwards what the actual radius would be. And took an average, and this is what we ended up with: 114, 203, and 338 micrometers. Gustaf then simulated all the 5 geometries. So the deep cracked ones and the shallow cracked ones, here we had the criterion that because the crack was modeled with a small notch. And here we had the criterion that the notch, the deformed notch should, or the deformed notch minus the initial notch should be larger than 4 times the initial notch. And then for the notched ones, we just used the radii that were given through the experiments. Those are the elastic parameters, so nothing special about them. And we used J2 plasticity. We had flow stress from the tensile testing, and we assumed no crack growth, so we could just use J2 plasticity. And now the simulation, I showed you contour plots of the maximum first principle stress. This is now for the deep cracked specimen at 25 kilonewton per meter. Yeah, you can see we have a peak spread, or the peak of the first principle stress just in front of the crack tip. So this is just as we all know and have seen before. If we now look at this largest notched specimen, we can see now that the peak is not getting as large. It's not getting as large stresses. The peak is also a bit further away from the notch tip. So the question was then, okay, is this altered stress state enough for the weakest link models then to have an accurate prediction for the notched specimens? And those are the results. We have these 5 distributions. Again, you can see that those are scattered. What we also see is that the material is really homogeneous, which is really nice. It was just as promised from Brittle. Those were the cracked specimens. This is, as we have seen in other materials before, we're not surprised by this. And here now we see exactly this effect for these notched specimens, this increased fracture toughness. And also, it's quite dependent on the radius. The larger the radius, the larger the fracture toughness. So then we fitted first the Berimin model to the cracked state here. And yeah, we knew this was possible. We have done this before. And the next step was then to predict these notched specimens. And we can see this is really conservative. Now we have also tried other things then. So of course, we have then at some point tried to predict or to fit not only these 2 curves, but also maybe one of the radius, but it's really, I really tried a lot, but it's not possible. And it's also interesting, also when we found maybe different fitting parameters, I didn't find the same as my master thesis student, Gustaf. And still the curves, they look the same, also the notched ones. So then we tried, okay, what if we take into account these strain effects? And the curves look really similar. So including the strain doesn't really change anything. And then I added some modification to the Faleskog model. And this was, for example, when we look at the number of micro cracks over effective plastic strain, there's some research since the 60s, I think. We see first that in the beginning, it's the number of micro cracks doesn't increase directly. At some point, we have this linear part, and then it becomes almost constant. So I tried all these things. I replaced the linear function first by a strain integral. So we have an incremental description to take into account the history. Then I tried to deactivate the microcrack nucleation for high plastic strains, because here we are basically we're not getting any more microcracks. And also introduction of a threshold strain here. I will say now, the master thesis has presented the results last week on Friday, and this I've all done since then. Maybe I'll come up with something new next week, I don't know. But qualitatively, all the plots will look the same. So the conclusions here. We have done Brittle fracture toughness tests for 5 different geometries where 3 were notched. The notches increase the brittle fracture toughness compared to the cracked specimens drastically. The scatter looks quite uninfluenced though. Neither the Berimin nor the Faleskog model are able to predict the fracture toughness of the notched specimens. And the next step would be now, because we have all these nice specimens, now it would be nice to do some fractography on the fracture surfaces to find the initiation points. And then what I really want to do is, it's maybe a dream of mine, is to really look at the hazard fields. How do they look like? Is the highest failure probability really there where we observe these fracture initiation points, and then especially then also for the notched specimens? And maybe we will be able to redefine the hazard function and find one that can predict these notch effects as well. So thank you.